Swayam Prabha. Digital India. Educated India.
Well, if you have a random variable with a probability distribution of some kind, the mean value, the mean square value, the mean cube value, they're all called the moments of this distribution. And given the moments, the interesting question is, can you recreate the distribution itself? It's called the problem of moments. Because experimentally, what you measure are the moments always. First moment, second moment, etc. Very roughly speaking, the first moment gives you the mean, of course, by definition. The second moment helps you find the variance. The third moment tells you if the distribution is symmetric about some central point or not, whether it's skewed or symmetric. The fourth moment tells you how fat or thin it is, how much does it weigh, small values about the mean or large values about the mean, and so on. So they have physical meaning, all these guys. Let's calculate this quantity for our distribution here. How do I calculate h squared? So let me write down again what our f of x was, generating function was. This was equal to px plus q to the power n, and the mean value of h is equal to np. How do I find h squared? I need this. How do I find this? What happens if I differentiate this function twice?
And into n minus 1 into p square into p x plus q whole part.
Yeah, so let's write down f of x. I differentiate twice, I end up with this. Each time a power of this goes on decreasing. What's f double prime of 1?
H into h.
So there's the first term which is h squared p of h, which is the mean square value. Minus h times p of h, which is the mean value. That's f double prime of 1. Let's calculate that here. F prime of x was equal to np px plus q to n minus 1. So there we have it. What's f double prime of 1? F double prime of 1 is equal to h average squared minus h. So what happens if I put that in here? So I substitute there and I get this quantity. That's this term plus H. And this cancels this. NP minus NP squared is NP times 1 minus P.
Yes.
But what's 1 minus P?
Q.
Q. So at last we have our result which says the variance of H so it's the number of trials multiplied by the probability of success in any one trial multiplied by the probability of failure in any one trial. That measures the scatter. So the relative fluctuation in H equal to the standard deviation of H divided by the mean value of H. In any random variable, the relative fluctuation is measured. The measure of it is how much there is, what's the standard deviation divided by the mean, the ratio of this quantity. What is it in our Bernoulli trial problem? What's the standard deviation? The variance is sitting here. What's the standard deviation? The square root of this guy. So this is equal to square root of NPQ. What's the mean? NP. That's what happens to the gas in this room. Goes like 1 over square root of NP, the relative fluctuation. That's the number of molecules in this room. Okay? How many molecules are there in this room? Approximately. 10 times Avogadro's number? 10 to the 24. So the relative fluctuation in the density is 1 part in 10 to the 12. Because it's 1 over square root of 10 to the 24. That's how good thermodynamics is. Which is why we get away with it. Because the fluctuation is 1 part in 10 to the 12. That's why most thermodynamic variables will be at their average values. The variation is very, very small. Okay? When they're all moving independent of each other, this factor, this n in the denominator, is what creates stability. It's clear? It's very crucial. Of course, I've done it for the binomial distribution. You should be able to do it for other distributions as well. But there's one little formula I'll write down, then we'll take a little break. And that is how to find large factorials. The factorial function increases very rapidly. The factorial of an integer, positive integer, increases very rapidly as the integer increases. In your calculators, which you've got up to power, you can write numbers up to 10 to the power 99. After 70 or so, you can't calculate factorials using that. The number exceeds 10 to the 99. Okay? But there's a formula called Stirling's formula, called Stirling's approximation, which is really should be called a Stirling formula, which is an asymptotic formula for n factorial, and it goes like this. It says n factorial approximately n to the power n That is clearly an overestimate because n factorial is 1, 2, 3, 4 up to n. You replace all the factors by n, you get n to the power n. That's clearly an overestimate. So it's got to be cut down, and it's cut down by the factor e to the minus n. That also increases with n, decreases with n exponentially, e to the minus n. Square root of 2 pi n 1 plus 1 over 12n plus order of 1 over n squared. This portion without the bracket is called Stirling's formula. You can derive it quite easily, but you need to know what's called Gaussian integrals, so we won't do that here. But it's worth remembering. The formula is written down for log n factorial actually. Log n factorial becomes n log n minus n plus half log 2 pi n. It's a small correction compared to this here. How good is Stirling's formula for large? For large n, you can see how good it is very easily. But suppose n is the smallest possible value, 1. What does it say? This equal to that, what does it imply? You have no business applying Stirling's formula for 1 because 1 factorial is 1, that's the end of it. But if I use Stirling's formula, what do you get on the right hand side? So the question asked is E right? You're guaranteed that it's 90% correct because the correction is 1 plus 1 over 12n, which in this case is 1 over 12, which is 8% or so. So this is correct to 92%. Even at n equal to 1. At n equal to 10, of course, it becomes immediately much more accurate. But by the time n hits 100 or so, it's correct to 4 or 5 decimal places. And when n hits Avogadro's number, it's correct. The error is completely negligible. Okay.
So why not taking 1 plus 1 by 12 n plus order of 1 plus n 1 by
Yeah, that's an asymptotic series developed for n factorial. Okay. It's a series which is, as n becomes larger and larger, fewer and fewer terms will give you the right value. It's an approximation. It's an explicit expansion for n factorial. Okay, I withdraw that statement. Okay, I don't want to claim, I don't want to include that here because.
So can you at least tell it again so we can go back to the hostel if not possible, but also we can discuss later.
Yeah, I should tell you where this formula comes from. That will tell you that clearly. Okay, let me tell you where this comes from. I wanted to do something else, but the story starts like this. Suppose I plot as a function of n, I plot n factorial. What do you get? At n equal to 0, 1 factorial is by definition 1. What's 2 factorial? 2 factorial is 2. So let me start like this. I'll plot these guys. Let me define. No matter where I start, I have to assume that you know Gaussian integrals. I don't want to do that. Okay, so you have 1, 2, and then it becomes 3 factorial is 6, 4 factorial is 24, etc. It increases extremely rapidly, like this, very rapidly. The question you can ask is there a function which interpolates between these points? Can I define a function which interpolates such that whenever the argument takes an integer, positive integer value, it gives you the factorial. Otherwise, it's a function which interpolates. Continuous function. Such a function exists and it's obtained as follows. 2 questions. Is there such a function? And if there is it unique?
Unique, why does it have to be unique?
It cannot.
If it's not unique, then I can always add sine pi n to it, and when n is an integer, that vanishes. So it could do this. It will go through like this. It matches all these integer points, but it's a different function altogether. You need uniqueness, otherwise you're in trouble.
So why do we multiply with sine 2 pi n?
Why do we what?
You said you multiply it with sine 2 pi n.
No, if you give me the value of a function at all the positive integers, or all the integers for that matter, it's a discrete set of points. Infinite set, but discrete set. The question is there a function that I can use to interpolate between these points? The function takes the values, prescribed values at all the integer values of the argument, and in between it's something else. It's a continuous function. If it cannot be unique, because you can always add to such a function. You come along, give me this function, and I'll add sine n pi to it. And when n is an integer, sine n pi is 0. But it's a very different function from what you gave me, right? So I need further conditions. I need asymptotic conditions to make it unique. And for the gamma function, Euler's gamma function, that's precisely what happens. And I'll explain where this comes from. This integral is the basic integral. It's called the Euler integral of the second kind, 0 to dx. Okay. You can easily check by integration by parts that this follows. In fact, this formula defines 0 factorial. We take 0 factorial to be 1, it comes from here. It comes from here. Otherwise, how will you tell me what is 0 factorial?
Is this from where the Taylor series?
The Taylor series is for general functions. This is a particular integral. This is defined to be equal to something called a gamma function. It's called the Euler gamma function. And it's defined to be this, but now comes the interesting part. I can make n non-integer and it will still work. It's the definition of this gamma of n. So I can define a gamma of, let me use t as the integration variable. And then if I make this x, this is valid when x is equal to 0, 1, 2, etc.
Same gamma function that was referred by Ramanujan in his first letter to Hart.
Yeah. It was introduced by Euler a couple of centuries earlier. That's the correct interpolation, and it satisfies all the required properties. So one uses that in order to estimate n factorial. You ask what happens to this as x becomes very large. And the way it's done is physically very simple. Look at the factor t to the power x e to the power minus t for large values of x. What does this function look like in the t plane? What does t to the x look like where x is very large? It's a sharply increasing function. What does e to the minus t do as t become for values of t? Starts one. You're multiplying the two. At the origin, it is still 0 because you 0 multiplied by a finite value is 0. At infinity, this dominates over that completely. Right? So this kills it. No matter how high the power of t, e to the power x is negligible compared to e to the minus t. Exponential always wins. Roughly speaking, the exponential is stronger than the power is stronger than the log. That's all of calculus in a nutshell. So you have a function, you have an integrand, which is the product of a sharply increasing function and times a sharply decreasing function. At 0, this function dominates and gives you 0 as a product. At infinity, this exponential dominates and gives you 0 as a value. So the product must do this. It must rise and then fall. Right? And the greater x becomes, the sharper this becomes. So it becomes sharper and sharper. And you can do a Gaussian integral. This goes like e to the minus x squared. You can do that and retain the leading terms. So that's how Stirling's formula is obtained. And you can find corrections to it and so on, and that gives you the 1 over 12n plus 1 over n squared, etc. etc. Let's have some tea or something like that. Let's break for a few minutes. Do you have an extramural today? Or today you're going home?
So how do we know that this Euler's gamma function is the best way to interpret it? Like is there a proof?
This function, gamma function itself, let me plot the gamma function for you. It's defined by this integral to start with. It's defined by this to start with, but you notice that with this integral definition, I don't need x to be a positive integer. It's still valid. X could in fact become complex as long as the real part of x is positive. And then I can do what's called analytic continuation. So if you actually plotted this gamma function, it looks very funny. It has a minimum between 1 and 2 and keeps going to infinity, exponentially fast. And its uniqueness is not in terms of gamma function, but the reciprocal of the gamma function. That looks like it's unique. Satisfy the asymptotic bounds. Okay. Very useful function. So the factorial generalizes. And by the way, this integral is the reason why 0 factorial is defined as 1. It's consistent with this integral. So once you have this, you can ask what is gamma of minus 1, minus 2, etc. and they're all infinite. Diverges at all the 0.
According to that, minus the negative decimals will give you a value.
Yeah, it gives you values, sure. But all at 0 and negative integers, it's divergent. So it's infinite. All positive integers, it's fine. Okay, let's take a little break and come back. Is there any tea today?
There is tea.
We'll have a small break.
So there is tea actually.
Okay, okay. We saw, we looked at some properties of the binomial distribution using this coin toss experiment. You can ask another kind of question with the same coin toss. So I have a coin in which the probability of a head is little p and tail is little q, which is 1 minus p. And I ask the question, my experiment is the following. I start tossing this coin and I stop as soon as I hit a head for the first time. The first time I might get tails, then I continue to toss till I get heads. The first time I get a head, I stop.
Yes, sir.
Right? Let me get a head for the first time in the nth toss. N runs 1, 2, 3, 4, etc. Then I ask, what is the probability P of n? That means I must get a head for the first time in the nth toss. What's the probability of that?
1 by 2 times.
1 by 2 power n minus.
Why do you say that?
So because every single
No,
one
little
will
p,
get-
little p and little q.
Okay, so little q probability of getting heads, right? So q to the power n minus 1.
So the first toss must be a tail q, n minus 1 factors here, multiplied by p, a success at last. Does everyone agree?
Yes, sir.
That's what these people proposed. So all I've done is to write. The first time you get tail, you get probability q. The second time tail, probability q, etc. N minus 1 times. The nth toss, you get a p. Is this probability normalized to 1? What are the possibilities for little n? What are the values allowed?
0 to capital N.
There's no capital N here now. Just one coin.
Okay, then definitely not normal.
I can go on getting tails. I may be very unlucky. I may get a million tails before I get a head. 0 to infinity.
But how does 0? By 0 do we mean every
1
single
to
coin
infinity.
tosses?
1 to infinity.
1 to infinity, yeah.
Because n can take the values. This is a geometric series which converges because q is less than 1. 1 plus q squared all the way to infinity is 1 over 1 minus q. Put that in and you get 1. What's the mean number of tosses? Mean number, average number. On average, how many times do I have to toss the coin to get a head for the first time?
N e to the power n.
You have to multiply by n.
Yeah.
But how do you do that sum? It's an arithmetico-geometric series. You have to do that. But let's find the generating function for this. Let's find the generating function. So I define the generating function f of x summation n equal to 1 to infinity p of n x to the power n. That's my definition of the generating function. P of n is p q to the n minus 1 x to the power n. I pull out a px. Just a geometric series.
Yes, sir.
What's f of 1? What should it be?
P by 1.
Should be 1. Is it 1?
It is 1, sir. It is 1.
1 minus q is p.
Yes, sir. Yes, sir.
It's 1, so it's normalized, right? What's the mean number now? Take the derivative of f of x at x equal to 1. Just 1 over p. Is this a physical answer? If a coin is fair, what does it say? It says on the average you have to toss the coin twice to get a head for the first time. That's the average number.
Yes.
Yeah, yeah.
What happens if little p goes to 0?
You will never get.
You're never going to get a head.
Yes, sir.
So it goes on to infinity. What happens if p is 1?
The first try.
The first try you get a head. So it's very physical. Now find the fluctuation about this point. Exercise, homework exercise. Find the standard deviation and the relative fluctuation.
Yes, sir.
So let's do a little more in this respect. Let's look at a random walk, which is exactly the problem of coin toss. Random walks have huge number of applications, so let's look at a random walk which does the following. Simple rules. I take a linear lattice, I take sites labeled by the integers 0, 2. Forever, it goes on forever. On the left hand side is the site -1, -2, goes on forever. And I start at 0, at t equal to 0. And my rule is the following. I flip a coin, a fair coin. If it's heads, I take one step to the right per unit time. If it's tails, I take one step to the left. The question is, what's the probability of being at any given site after n such steps? So the rule is the following. It's called a random walk. This is called a simple random walk. I toss a coin. If it's heads, I take a step to the right, to the next integer. If it's tails, I take a step back to the left, next integer. And I do this at the end of every 1 second. The question is, after n seconds, where am I?
It's average edge minus 1 minus average edge.
What is edge?
Again, edge is. Wait, it's edge.
What is the maximum I can be to the right?
So number of heads. Average
Yeah,
number
so-
of heads minus 1 minus average number of heads should give you the point you are at.
Yeah, but what's the exact factor? So let me call that probability. Let's take an arbitrary site, call it j. There's j plus 1, j plus 2 going all the way to infinity, and there's j minus 1, j minus 2 going all the way to minus infinity. Okay. Then I ask, what is the probability that in n steps I am at the point j? I'll put this n inside here so that it doesn't clutter up the board. What is the probability that after n steps I am at the point j? So what's the random variable here? Because n is given to you, little n is given to you. J is the random variable, right? What is this equal to? Certainly, in n steps, can I go further? Can I go beyond n?
No, sir.
Right? In n steps, how can I go beyond n? I can go to any value of j up to n, right? So this is equal to 0 if mod j is greater than n. J can be negative. I can't go below minus j minus n, and I can't go beyond plus n. Okay.
Yes, sir.
Suppose j is an even number. Can I reach it in an odd number of steps? Every second I have to take a step. If I want to reach 2, for instance, I can go 1, 2 in 2 steps. I can go 1, 2, 1, 2, 1, 2, 3. I can go in 4 steps.
So it only reaches an even number of steps.
It's clear that j and n must have the same parity. I cannot reach an odd numbered site in an even number of steps and an even site in an odd number of
Yes,
steps.
sir.
Yes.
Right?
Yes, sir.
So n and j must have the same parity.
Yes, sir.
So it's equal to 0.
So how would you mathematically represent different variables versus variables?
Exercise for you. Exercise for you.
I would get it like
N minus j must be an even number. Both must be even or both must be odd. So put that in there. Now suppose these conditions are all satisfied. Mod j is less than n. Then what happens? What's the answer? Clearly, if I start at 0, and here is the point j, let's take j to be positive for the moment, I must make at least j steps to the right. Otherwise, I can't reach j. But if I have a number n which is bigger than j, the remaining steps must be cancelling each other out. So I overshoot and I come back by cancelling. Right? So I must make at least j steps to the right. The probability of that is p to the power j. Probability of a step to the right is p, and I must make at least j steps to the right, so p to the j. How many steps does that leave for you? N minus j. But they must be equal and cancel. N and j must have the same parity. It must be an even number. So half of them must be steps to the right, half must be steps to the left in some order, and they cancel each other out. So this is j plus n minus j over 2 q to the power n minus j over 2. So this whole thing is p to the power, this is n plus j over 2. But it doesn't matter in what order I make these steps. I go right, left, etc. The total number of rights must be n plus j over 2, the number of lefts must be n minus j over 2. Exactly like our coin toss experiment, but in any order. Right? So the answer to our problem,
So why is it n minus j by 2?
I have n steps, of which I finish j of them by going to the right to j. That's the least number of right steps to the right you must have. Right? That leaves n minus j steps,
Yes.
because n is bigger than j.
Yes.
But these steps must be right and left in equal number.
Okay. Yes.
Right? So the number of steps to the right is j plus n minus j over 2, and the number of steps to the left is n minus j over 2. So the probability of being at any j in n steps, j comma n, I wrote n comma j, I'll take that back, j comma n, this should have been written j comma n. This is yet another binomial distribution. This is for all j such that mod j is less than or equal to n and n minus j is even. That's the solution to the simple random walk. Now you can compute mean square, mean cubed, and things like that. So take n, for instance, to be equal to 4, and on this lattice, and write down what these probabilities are. The question is, how long does it take to reach this point for the first time? So let's do that problem, and you'll see how powerful this whole thing is. The important assumption, physical assumption here, is that all these steps are independent of each other. Each time I toss a coin and decide, the individual steps are independent of each other, statistically independent, right? So let's do a baby problem and see how it is. I don't have an infinite lattice on both sides, so let's start with a linear lattice. Two sides. This is side 0, this is side 1. I start at t equal to 0 at the side 0. At the end of 1 times 1 second, I don't toss a coin, I move to the next side, 1. What is the mean time it takes to go from 0 to 1? Let me call it 0 to 1 mean time. It's equal to 1. There's nothing to be averaged over. At the end of one step, I move. Now let me add a 2.
So why would it not have gone to -1 and come back to 0?
I'm just using a simpler form so that I don't have negative numbers. Otherwise, it's just algebraic nuisance. I put a boundary here. I put a wall here and say there's nothing to the left. This is twice the distance. And now I ask, what is the mean time it takes to reach 2 for the first time? T 0 to 2. So the moment I walk and hit the side 2, I stop. The question is, what is the mean time I take to reach 2? It is twice the distance of 0 to 1. And now you have an infinite number of possibilities. You will go from 0 to 1 at the end of one time step. Then from 1, you toss a coin. With probability half, you go here and then the matter is over. Or with probability half, you go back here. And you keep doing this back and forth. Forever you may do this. And you have to add all those probabilities and say what the mean value is.
But it will still converge to. It will still converge to a number.
You're not sure. You're not sure.
So because.
What's the guarantee that it's not going on doing this all the time?
Yes, it is.
You have to weight it on average. Tackling this is not a trivial problem at all. Okay? But I use the fact that the different walks are all linearly independent of each other, statistically independent of each other.
Yes, sir.
Right?
Yes, sir.
Every step is statistically independent of every other step. Okay. Then I argue like this. This number, so let me call it T0 to show that it's the probability of hitting 2 for the, I want to hit 2 for the first time. The mean time to hit 2 for the first time starting at 0. Let me call that T0. With probability 1, at the end of one time step, I go to site 1. So with probability 1, I go to site T1 multiplied by T1. Right? So T0 is equal to 1 plus T1 . T1 is the probability that I start at 1 and hit 2 for the first time. Mean value, mean time. I take one time step to go to 1, and then from there, it's anything is fair. T1 is the mean time to hit this point. But what is T1? I'm here and I want the mean time to hit this point for the first time. There are two possibilities from here. I either move to the left to 0, back to 0, start all over again, or I hit this 2 right away with probability half in each case. Okay. So it's half 1 plus T0, because 1/2 probability, one step is used up in going back to T0, and then it's back to square 1 plus half.
So could you repeat that?
From T0, I have only one possibility.
Yes, sir.
I take with probability 1, I hit 1.
Yes, sir.
That takes one time step, so I count that one time step. And then I'm at T1, and the mean time to hit 2 from the site 1 is denoted by T1.
Yes, sir. Okay.
So it's this,
Yes,
right?
sir.
Then I go to T1,
Yes, sir.
and from T1 there are two possibilities in the first step. Either I hit the 2 straight away, probability half
Understand, sir.
times 1, plus with probability half, I get back to T0, but wasting a time step,
Yes, sir.
and then I'm back to T1,
Yes, sir.
right? So this is equal to T0 over 2 plus 1. So it implies that T0 over 2 is equal to 2. So it takes me 4 times as long to go twice as far. So this is the basis of diffusion. Diffusion the envelope increases like the square root of the time. If you put a drop of ink in a beaker of water and you see this pattern growing, roughly circular pattern, spherical pattern, the extent of that will increase like the square root of time if there's pure molecular diffusion. Because if I walk at constant speed v, I walk for time t, the distance I cover is the speed times the time, or whatever, right? I go linearly in time. The distance covered is linearly increasing with time. But if I walk without purpose, I vacillate back and forth, it takes me 4 times as long to go twice as far. So if you're drunk, you take much longer to get home. It's called a drunkard's walk or a random walk. But you can play this game in more complicated situations. Here's one which I'm going to leave as a homework problem for you. There are objects called fractals which model substrates. And here's a simple fractal. So you have a triangle, unit side. And you have a random walker on this triangle. So the walker starts at this point, 1, and has to hit either 2 or 3. These are traps. And he hits either 2 or 3, the walk ends. And then he moves along each path with equal probability. As many paths as there are, he moves with equal probability. What is the mean time to start at 1 and hit either 2 or 3? 1. The first time step, you either hit this point or this point.
Yes, sir.
Okay. Now I come and double the size of this triangle and decorate the sides of the triangle by another set of sides. Same rule as before. I do random walk on this situation, this thing. This is called a generation 1 Sierpinski gasket, but that's not very important. You go on iterating this procedure of decoration, expansion and decoration, you end up with what's called a fractal. Now the question is the following. To get to either of these straps took me unit time 1. I do the same thing here. I start at 1 and I want to know what is T1. To hit either 4 or 5. And I have to write a set of equations. So T1 is equal to, with probability half, I go to 2. So half 1 plus T2. Plus with probability half, I go to 3, 1 plus T3. Each time T subscript denotes the mean time it takes from that side to hit the traps at the end. These traps are now twice as far away as in this case here. So that's the equation for T1. What's the equation for T2? With probability 1/4 he goes to 1, 1/4 he goes to 3, 1/4 he goes to 5, 1/4 he goes to the trap at 4. So it's equal to 1/4 1 plus T1 plus 1/4 1 plus T3 plus 1/4 1 plus T5 plus 1/4 times 1 because he's hit 4. Similarly, you must write an equation for T3, you must write an equation for T5. Equations for T4 and 6 are not needed because they're themselves 0. Meantime, you're already there. Okay. But there's a symmetry in this problem between left and right. So it's clear by looking at it, you're starting at a symmetric point with respect to 2 and 3 and with respect to the traps here. So it's obvious that T2 and T3 must be the same. Right? So you can simplify a little bit. So this is the same as T2. T5 is a different story. T5 with probability 1/4 you hit this point, 1/4 you hit this point in one step, and then 1/4, 1 plus T3, 1 plus T2. So you write one more equation and solve for all these for T1. Do that as a homework exercise.
So it's T5 1/8 or is it 1/6?
Sorry, which one?
T5, right? Yeah, T1 and T2.
T5. 1/4 times 1 he gets to 4 plus 1/4 times 1 he gets to 6 plus 1/4 times 1 plus T2 and the same thing with T3, but T3 and T2 are equal, so it's just this. Always you must check that this normalizes to 1. 1/4 plus 1/4 plus half is 1.
But how did 1/4 come in T2, sir?
Because the rule is that if there's a site for which there are n nearest neighbors, he jumps to any one of them with probability 1/n. It's completely unbiased. Chooses each path that is in front of him with equal probability. So if you solve for T1, you have actually solved a fairly non-trivial random walk problem because the guy could have been stuck here. He could just keep going in this loop forever without hitting this. But you're guaranteed that doesn't happen. You're guaranteed that he's going to hit 4 or 5 eventually, and you can find out how long it takes to do that. T4 and T6 are twice as far away from 1 as in this case. So this problem solves the problem of what happened, how much time does it take to go twice as far? Pardon me?
Can it be 16?
Can it be?
16, sir? It's just a guess. 16.
No, it's not 16.
8?
Pardon me?
8?
You're taking a guess? That's an intelligent guess. What are your guesses?
I'm thinking on
Right.
the 4, sir, because the rate of diffusion for that one itself was 4, sir.
It's not a linear lattice. There's a loop here. There's a loop here. You're going to add over all those things. You write in the probabilities for them. It's a mess. But this is a simple argument to find the mean values. If it's a simple random walk on a linear lattice, it was square. It went like the square. Right? To go to twice as far, it took 4 times as long. So the factor was the square of the. On a linear lattice, on this lattice, 0, 1, 2, 3 up to n, to get to the point j, the mean time n is equal to j squared. Just the square of the site number. So to go twice as far, it takes 4 times as long. In this problem, it's a simple set of algebraic equations which you can check and work out. It turns out that T1 is actually 5. So it takes 5 times as long to go twice as far on this fractal. And this extrapolates. The next generation fractal will look like this. Etc. So the number of sites increases exponentially, 3 to the power something or the other, as the generation increases. And then to go twice as far, it scales exactly like log 5 over log 2. 5 is the scaling factor. So the next time, if this is 5 units, it will be, as you increase the number of units here, it increases like 5 times 4, 5, 4.
It's not drawing another triangle inside. Inside like the cycle.
That's the rule for creating this fractal. There are an infinite number of fractals you can create. Okay, I shouldn't have used, I withdraw that word.
No, see, I know intuitive definition. I don't know formal definition.
So, after we get T1, T2, and T5, what is the general mechanism, sir? What are we doing? Are we adding everything or are we substituting things?
This is not a straight path. It's got loops in it.
Yes, sir. I mean, like for the simpler one, the like 4 triangles ones.
The linear one.
Duration, this one, sir. This one.
The linear one.
Yes, sir, for that one.
Yeah, what about it?
So, sir, how are you simplifying it down to get T1 is equal to 5? Like, are you adding T1, T2, T5, or are you?
No. I'm asking for the first mean time it takes to go for the first time from 1 to either of these two ends.
Yes, sir.
That's the question we are solving.
Yes, sir.
By arguing what happens in the first step. To go from here to here, you have to take the first step either to 2 or 3. And then the problem is repeated all over again. Oh, let me illustrate perhaps I should do that. Let me use a simpler example of what is happening, what these iterative things are all about. So let's consider a linear lattice. This is site 0, this is site 1, this is site 2, and so on. This goes on all the way to minus infinity. I have a walker who starts in this linear lattice, takes a step to the right or left with given probabilities P and Q. So he goes to the right with probability P, goes to the left with probability Q, which is 1 minus P at each time step. At t equal to 0, he starts at 0. At 1, unfortunately for him, there's a tiger waiting. or a cliff. So this is the tiger. If he goes to 1, he's dead. Is he going to escape or stay alive doing this random walk? What do you think?
P and Q. Yeah. So
Depends on P and Q. Is he likely to survive?
We are just considering -1, 0, and 1, right? No other points.
I want the escape probability. I want the probability that this fellow will escape altogether, no matter infinite number of steps. Is it possible to do it?
That be possible, yes.
Hmm?
It should be possible. Because
So if he's walking forever,
We're walking forever.
then he's got.
And we're walking forever, and there is no boundary here.
He will die.
If there's a barrier here, then with probability 1, he's going to fall into the trap sooner or later. But if this goes to minus infinity, he's got an infinite amount of space to escape. Let's calculate the escape probability. Okay? What is the escape probability? Or capture probability. So let me call capture probability C of P. C of P is the capture probability. C of 1 is obviously equal to 1. Because if he uses the coin which he gets hit the first time, he jumps to the right and falls down. That's the end of it. So intuitively it's clear that if P is less than a half, he might escape. Because the probability of going to the left is larger, he keeps going to the left all the time, he never comes back. There's a hope. But C of 1 is definitely 0. Definitely 1. So what would you write? What happens in the first step if he escapes? If he is captured? The probability is P. In step 1 he is gone. But if he takes a step to the left, that's with probability Q. And where does he find himself? He finds himself at -1. And then you want the probability that he gets captured at the site 1. So he needs to come to site 0 and then he must go to site 1. Now the situation, it's an infinite lattice on the left. So if you forget this site, the site 0 is situated with respect to 1, -1, in the same way as site 1 is situated with respect to 0. It's the same infinite lattice on the left hand side. So this has to be C squared of P. There's one C of P and then a total probability C squared of P. Right? So you have a quadratic equation for C of P.
So why would you not calculate for the next step and
Because
follow
all steps are independent of each other. C of P is the sum of a large number of terms, an infinite number of possible terms.
Yes, sir.
But the equation becomes nonlinear right away. But it's not over. So you have an equation that says QC squared minus C. Pardon me? How is the C squared? Now look at what happens at the first step if it's moved to the left. He is moved to -1. He has to be captured, he has to go there. The probability of going to 0 from -1 is the same as the probability of going from 0 to 1. Because it's an infinite lattice. So it's got to be squared. And then it gives you a quadratic equation. Right? And we know that C of 1 equal to 1. Right? We have to solve this differential, this quadratic equation. What's the solution?
Qs, sir.
Pardon me? 2Q. Which route are you going to choose?
1 minus. 1 minus. Because 1. Because
can have one
arithmetic can
here.
never be greater.
Can 4PQ ever be bigger than 1?
By 2Q.
It cannot be bigger than 1. It's equal to 1 only when you have P equal to Q equal to half. Okay, so this is the real radical. And it becomes bigger than 1 if you choose the plus sign. So you have to choose the minus sign. So
Sir, but you're dividing by 2Q, right?
that's okay.
It has to be less.
We already
Sir,
intuitively determined the half the derivative. Why it should work.
So what will the whole thing look like? What is the square root? Everything hinges on what the square root is. What is that square root? What's square root of 1 minus 4PQ? One minus 2p or mod of 1 minus 2p?
mod of 1.
Mod 1 minus 2p, yes, exactly. So to switch values. So you got two different answers for p less than half and p bigger than half. For p less than half, this guy is 1 minus 2p. For p greater than half, it's 2p minus 1. So what's the solution? It's not a straightforward function. Similarly for p less than half. So find what the solutions are and see what happens. So the capture probability, if you write it out, is like this as a function of p. It's a curve that starts like this and goes up, and then at p equal to half it hits 1 and remains 1. So this means if he uses a fair coin, he's dead. If he uses a biased coin, he has a hope of getting not captured, lower and lower probability. If he uses a completely unfair coin, biased in his favor to the left, he escapes. Otherwise, he's caught. So you can see this apparently simple problem is not all that trivial. Tell me how big is the atmosphere? How high does the atmosphere extend?
10 kilometers.
About 10 kilometers. Can we deduce that?
Wait.
Let's do it by dimensional analysis. What are the parameters in the problem? The height of the atmosphere. We want to see how high a molecule can go against the Earth's gravity. Molecules have kinetic energy, right, which depend on the temperature, etc. So from the energy, from K Boltzmann T, that's the amount of energy a particle has, a molecule has at temperature T. We'll assume the whole thing is at uniform temperature. What else can the height depend on? The mass of the particle, so the mass of a molecule, and of course little g. Can you form a quantity of dimensions length from this quantity? This is energy, mg is force.
So G is acceleration.
Pardon me?
So divide.
G is acceleration.
So kV minus g.
Mass times gravity is a force. So energy is kT over mg. This is equal to the height. That's the furthest you can have against gravity, on average. What's the value of this? What's the value of Boltzmann's constant? 10 to the minus 23 times 1 point whatever. 1 point what? 1.38 or something. It's not relevant. We want order of magnitude. What's T? About 300 Kelvin on the average. So about 10 to the 2 divided by mass of, what's the mass? Mass of a nitrogen molecule. Molecular weight? 28, about 30. Times the mass of a proton?
1.6 into 10 to the power minus 27.
G?
Approximately.
So this is 10 to the minus 21. Or 10 to the minus 25. Ten kilometers. About 10 kilometers. Okay, which is the right ballpark. It's not 1 kilometer, it's not 100 kilometers. It's about 10 kilometers, which is just about right. Right? Significant atmosphere lasts up to 10 kilometers. But the question is, what is the probability that a molecule has a height h above the ground? That requires a little bit of statistical mechanics. The probability that the molecule exists at a height z above the ground, P of z, probability density, is proportional to e to the power minus mg z over kt. It's called the barometric distribution. The density decreases exponentially. Okay. If you plot this as a function of z, apart from some normalization constant, it goes down like this. Proportional to e to the minus mg z over kt. Ratio of the potential energy divided by the kinetic energy due to temperature.
What equation is it? Name?
It's called the barometric distribution. It's a big assumption, it's a very simplified model, but it looks like this, exponentially. The density decreases exponentially as you go up, density of air. What is the most probable value?
Most probably
Where does P of z become maximum?
at the base.
At z equal to 0. So if everything were at the most probable value, all the molecules would be on the ground and we'd all die of suffocation. The fact that you have a distribution shows that there is a spread about the mean value, about the average. Fluctuations due to collisions and so on. 3 cheers to collisions because of them we live. If you didn't have fluctuations, but all random variables were at their most probable value, there'd be no fluctuations and we'd be dead. All the molecules would be on the ground. Proof that fluctuations exist is that we are alive and breathing. All the air doesn't condense into a small corner in that room with any significant probability. All the air doesn't fall onto the ground with significant probability, and we are alive and well. Find the mean and the mean square and scatter about the mean. Normalize this distribution to 1. Integrate over z from 0 to infinity. The answer must be 1. So that fixes the constant, and then find the generating function and the mean and mean square. Okay, let's stop there. Any other questions?
So I have a question regarding the special relativity term.
Okay.
So there, how did we? Okay, momentum of force, momentum you said was m naught v divided by square sine the square root of 1 minus v square by c square. How does this apply to a photon whose response is zero?
That formula is not true. For a photon, E is Cp.
Yes.
So the momentum is E over C.
Sir, but what is momentum?
What is momentum? That's a good question. I'm trying to see what the simple explanation. Yeah. Well, it's more than that. It's more than that. It requires me to use the concept of Lagrangian and Hamiltonian. That's the only language in which I know. Yeah. One thing is for sure, the momentum is not always equal to mass times the velocity. It's got physical dimensions of that. Linear momentum has physical dimensions of that, but angular momentum doesn't have those dimensions. Some other dimensions. You see, in general, what happens is any mechanical system can be described by a set of coordinates called degrees of freedom. And each coordinate has associated with it a conjugate variable called its conjugate momentum, obtained by a definite prescription from the so-called Lagrangian of the system. That's the true definition of the momentum, canonical momentum. In the simplest cases, it reduces to Newton's MV. And that's not true in general.
So how did Newton come up with momentum? Did he just empirically look at a lot of experiments and find this quantity be conserved, or did he have deductive reasoning for such?
I don't know the history of why. Actually, I'm not very sure about the history of how exactly he came out with his Newton's laws of motion. But there are accounts of this, historical accounts of this. Empirically, I mean, he did a lot of empiricism, definitely. Newton's first law was actually propounded by Galileo, so he knew that already. The insight was in the second law. The third law is conservation of linear momentum for two objects at a time, so that's again. To retrace what he did historically must have taken a very painful path to get to this thing here. For instance, just to give an example, not to divert the subject, but if you take a spherically symmetric mass distribution, the gravitational field outside is as if the entire mass were at the center, right? This result is trivially provable by calculus today by any of us in 10 minutes, right? But Newton took 16 years to deduce this fact because he didn't have the calculus developed at that time. So what was difficult in that time need not necessarily be difficult now. Besides, Newton had another handicap, which was that he had to prove everything by the so-called synthetic method of the Greeks, the Greek philosophy of deduction from Aristotle's days, because his contemporaries didn't believe in the calculus. So every time he gave a proof, such as for the elliptic orbits, etc., he had to give a geometrical proof for it. Today we don't do it that way at all. We use the calculus and that's the end of the matter.
What is a geometrical proof?
Properties of ellipses intersecting other planes and so on and so forth. A very elaborate geometrical proof he gave. But today we write down the differential equation and solve it and you get an ellipse as a solution. We don't even need that. We need the constants of the motion and that reduces immediately. Techniques have advanced considerably. So. Okay, thank you.
I would like to present my heartfelt thanks to Professor Balakrishnan for the extremely informative lecture. Your extremely detailed lecture on probability was fascinating and inspiring for us. I am sure that I speak for everyone when I say that this was a truly astounding lecture. Thank you.
Swayam Prabha. Digital India. Educated India.